So, we have been discussing the properties of the nucleus in the last class, and in this lecture we will look at the force that is holding the nucleus together, which is basically the strong nuclear force. We look at some of the properties of this force and then consider some simple system, nucleon system like the deuteron, before we further go into the other interactions like nuclear scatterings. So, as mentioned earlier, the nuclear force is a very short range force. Its influence is limited to something like 10 power minus 15 meters in range. So, if you take an atom, only within the nucleus the nuclear force is effective, and the electrons which are moving around will not see this force. So, this is short range, and it is stronger than the electromagnetic force. That is again evident because the strong nuclear force is holding the electrically charged protons together against the repulsive Coulombic force. Therefore, certainly it is much stronger than the electromagnetic force. Okay, and how do we know that it is not going beyond a certain this nuclear length scales? Otherwise, its influence will be visible. Say for example, in molecular formations, when atoms come together, if we know that strong nuclear force is stronger than the electromagnetic force, and if that can influence the at long ranges, then molecular formation will be dominated by the it would have been dominated by the strong nuclear force, not by the Coulombic force. But we know that we can explain the chemical bonds or the molecular formation coming together of the atoms to form molecules by using electromagnetic force. And then there are also nuclear scattering experiments which can determine the range of this nuclear force, and then from all these experiments we know now that it is a very short range force. And as I said a little ago, this nuclear force is not there between electrons. So, electrons are completely blind to this nuclear force. Again we know this from the atomic spectra, for example, because otherwise there are a lot of electrons in the atom and they could have interacted strongly. They could have interacted between each other strongly or with the nucleus strongly, but we do not see those, and because of this we now come to the conclusion that electrons have no strong nuclear interaction. It is also true from the other experimental results like electron scattering, etc., that we do not see, or we do not see the strong nuclear force between the electrons. Actually, when we come to the next topic, the particle physics, we will see that there are other particles like the electrons called muon, for example, or tau lepton, which is basically similar. These two, muon and tau lepton, are similar to electron, but slightly different in the mass, and also there are some other small differences, but for by and large they are similar to the electrons. They are collectively called leptons, and then none of these leptons take part in the strong interaction, nuclear strong interactions. The another property is that it is charge symmetric. Okay, by what? By that we mean, if I take proton and neutron, these are the two different nucleons that we know of, and that they are there in the nucleus, and they are both influenced by the strong interactions. Now, we can ask the question like if proton and neutron are different, how do they see these nuclear force? Is there any difference that the nuclear force, strong force, which the proton and proton see together and a neutron and neutron see together? Or when I actually change the species from neutron to proton, is there any difference in the interaction, nuclear interaction? Answer is no, that it is the same, it is symmetric under the NP exchange, and this loosely we can call this the charge, nuclear charge at that level. So, here the charge actually means whether it is proton or neutron. So, there is a symmetry, the strong interaction is symmetric under such an interaction exchange, or the between the proton and proton pair and neutron pair. And there is also, and it's actually we can take this slightly beyond this charge symmetry. We can actually say that it is completely independent of the charge. It does not care about whether it is proton and proton interacting, or proton and neutron interacting, or neutron and neutron interacting. It is all expected to be the same. In fact, it is experimentally now proved that it is the same. But if you take a proton and proton, they also have, in addition to the nuclear force, it also has the electromagnetic force, and therefore, there will certainly be difference in the total interaction of the proton and neutron and system, or the neutron and proton system. But since we know what exactly is the Coulomb interaction, we can compute that, and then once we make the correction for that, it is found that the strong interaction part of proton, neutron and neutron interactions the same. So, it is actually completely independent of this charge, independent of the fact whether it is a neutron or whether it is a proton. And another property is that actually it depends on the nuclear spin. I mean, nucleons has a particular spin, but when it comes together or when they interact, it is the relative orientation of the spin that will matter. So, for example, the spin orientation in the of the neutron and proton in deuteron is found to be parallel to each other. That means that total spin of the neutron is equal to 1, and the individual, the nucleons like neutron and proton will have the spins aligned parallel to each other, not opposite to each other. And in fact, if you compute the energy of different systems, nuclear systems with different orientations of the spin, you will see that the energy of the system, bound system, depends on whether the spins are parallelly aligned or oppositely aligned, or if you have more than one, then different combinations of these spin orientations. So, energy will depend on that, and it so happens that if you take a the proton and a neutron, then the lowest energy bound state is found with parallel spin arrangement. And if you take antiparallel neutron and proton system, antiparallel spins for this, then the energies are beyond larger, and therefore, it cannot actually even form bound state. We have not seen any bound state, any such bound state in nature. Okay, so, the next thing is another very important aspect of this nuclear force, which is that it deviates from its central nature. What do you mean by central force? If you have a force in between two particles, which depends only on the distance between these two particles and not any other orientation, say, then it actually is called central. For example, the gravitational force is central, because if you consider Sun Earth system, the gravitational interaction of the Sun Earth system depends only on the relative position, or how far is the Earth from Sun is what matters, not at in a particular coordinate system what angle or what polar angle or what azimuthal angle. It does not depend on that, it only depends on the r coordinate in the spherical polar coordinate system. So, that is a central force which is spherically symmetric, and one of the consequences of this, as you must have already learned in classical gravitational classical mechanics under the central forces, or in the case of Coulomb forces, that central force lead to angular momentum conservation, or the angular momentum of the system is then constant for a particular, once you form the system, the angular momentum remains there, it is a constant thing, and it has a particular value. Therefore, you can always ask the question like, what is the angular momentum of the system, relative angular momentum of the system. and then you will get an answer, some number, which is a conserved quantity. But in the case of nucleon system, it is not strictly central, and for example, in the case of a deuteron, you will see that there is an admixture of two different angular momentum values, or the wave function, which actually speaks about the state of the system, physical state of the deuteron, can be either in L equal to 0, or the 0 angular momentum, relative angular momentum between n and p can be 0, or it can be 2, or it can be a combination of these two. And in fact, it is found that 96% of the time this is actually L equal to 0 state, and then 4% it is actually in the L equal to 2 state. That is how the wave function of the angular deuteron is. And this measurement, this can be actually experimentally determined using various methods, for example, using a measurement of the magnetic dipole moment, which depends on what the angular momentum, relative angular momentum is. We will actually come to this this magnetic dipole moment of the deuteron. A little more details of this will be discussed when we actually discuss the deuteron system. Okay. All right. So, another property is that the nuclear force, strong force, though attractive, it is not attractive all the way down to small distances. So, if you take say proton and a proton, bring them together nearer and nearer and nearer, the force will actually increase. Okay. It will be you will see that there is a attractive force between these two, which is actually even stronger than the electromagnetic force. But you will see that beyond the distance, okay, these nucleons repel. Otherwise, say for example, you take a large collection of these protons like a big uranium nucleus, protons and neutrons in that nucleus, there are many of them, and if you have stronger forces, this force, nuclear strong force, attractive all the way down to very small distances towards the center of the nucleus, you will see that this has large density, because the force is stronger there, and then lot of these nucleons are there, and then they are all attracting each other and then coming together, and towards the, and when you go away from the center, there should be a decrease in the density, nuclear density. But this is unlike the case that we found experimentally. Experimentally, we have found something constant density, matter and charge density for the nuclear. This actually tells us that we have, as the nucleons come too close to each other, they actually do not allow each other to come any further nearer to them, to each other. This is actually kind of a repulsive nature of the strong interaction when you go to very small length scales. So, this actually prevents the collapse of the nucleus and nucleons being smashing into each other. Okay. So, this are some of the properties that by and large we can associate to nucleus or any general nuclear force in general between any system of nucleons. And we will study some of these in a little more detail by considering some nuclear systems. We will first consider bound state of the nucleus, which is basically the simplest one that we can think about is deuteron. It consists of a proton and a neutron, and when they are bound to each other, certainly they should have energy smaller than the energy of the neutron and proton, free neutron and proton put together. We already discussed in the last class the binding energy of a nucleus or bound nucleon system. So, the binding energy of a deuteron is an extremely or a very precisely measured quantity. We can measure that very precisely, and this leads to a value of say 2.224575 plus or minus 0.0000050 zeros and 9 MeV. So, this in this 2.224575 only the last digit is not certain. So, this is a, but this is actually I am quoting a particular result which is published in Nuclear Physics A 380 volume 380 and in 1982 page number 261 of the journal. And you can also look at other results and then kind of that will all be similar kind of this one and then with similar precisions. So, it is actually a very high, very precisely measured quantity. Now, another property of this nucleon system, the deuteron, is its spin. So, let us look at the spin of the deuteron. Deuteron has neutron in it, okay, and the spin of the neutron is, let me denote it by Sn, its actual value is h cross by 2 and spin of proton is, let me denote it by Sp, it is again a spin half particle. So, these two are the constituents of this deuteron. So, certainly when we talk about the total spin of deuteron, the spins of the neutron and proton will contribute to it. Not only this, we can also think about relative angular momentum, orbital angular momentum of this relative orbital angular momentum of neutron and proton. So, let me denote it by L, and then the total of these. When I say total, I mean the you have to add these angular momenta according to the angular momentum addition rules of quantum mechanics, and then the total of this, let me denote it by I, which is S plus or Sn plus Sp plus L added according to angular momentum addition rules of quantum mechanics. Okay. So, let us look at the spin part of this. Okay. So, spin part, which I by which I mean the contribution to the deuteron spin due to the spins of the neutron and proton. So, S is equal to Sn plus Sp added again according to the angular momentum addition rules of quantum mechanics, which says that if Sn and Sp have values Sn and Sp without the vector sign now, the magnitude of that, then the total spin can have values ranging from Sn minus Sp, the magnitude of this, okay, or the absolute value of this, and then increase it in steps of 1 and go up to Sn plus Sp. So, these are the values of S that are allowed according to the rule of quantum mechanics, angular momentum additions of the quantum mechanics. So, in steps of 1. Okay. So, in units of, so we will be working in units of h cross actually. So, we will not put h cross everywhere, we will assume that that is there and then we will write everything in the unit where h cross is equal to 1. So, S can be Sn and Sp are half each. So, Sn minus Sp is equal to 0 and Sn plus Sp is half plus half equal to 1, since there is nothing in between which differs by 1 unit. So, we have S either equal to 0 or equal to 1. Then you can ask the question, what is the measured spin of deuteron, the value of it, and answer is 1. It is experimentally found that it is equal to 1. So, as I said, there is spin part and there is also the relative orbital angular momentum part of this, and since I is equal to 1 as measured and since S is equal to 0 or 1, relative angular momentum between n and p, say L, can be different values, according to the following. Again, we will look at the angular momentum additions. So, firstly, L can actually have values 0, 1, 2, 3, etc. Now, case 1, let us take S is equal to 0 case. We want I which is equal to S minus L to S plus L to be equal to 1, 1 equal to I equal to this. Okay. So, since S is equal to 0, the only allowed value of L is equal to 1. Okay. Now, let us take the next case. So, case 2, where we have now S is equal to 1, then again 1 equal to I equal to S minus L up to S plus L, and I can have L equal to 0. In that case, I is equal to 1, because L equal to 0 plus S is equal to 1 will give me I equal to 1, and L equal to 1 will give me, it could be I equal to S minus L which is equal to 0, and then steps of 1. So, 0 plus 1 is 1, 0. So, 1 plus 1 is 2, which is equal to S plus L. So, I can have value 0, 1, 2. So, 1 which is experimentally measured value is there in this combination of L and S as well. If you take L equal to 2, then that will give I possible I values as 1 which is L minus S, and then plus 1 which is 2, and then 3 which is L plus S 2 plus 1. These are the allowed possible I values, and then I equal to 1 is again there. So, that is possible, but if you go anything beyond this, say L equal to 3, this will actually give you I value starting from 2, 3, 4, etc. So, this is not possible, or any other L larger than 2 is not possible. So, we can have system where L is equal to, so conclusion from all this whatever we discussed just now is that we can have orbital angular momentum of the neutron proton in the deuteron to be either 0 or 0, 1 or 2. It cannot be larger than 2. So, that is the conclusion. But now there are further other considerations. So, which will tell us that we can restrict this further, and then we will see that parity consideration, for example, will restrict this. So, let us consider that parity. What is parity? You must have come across with parity operation in your quantum mechanics class or other places. Basically, it is inversion of space coordinates. So, if you take x, y, z as your coordinate system, x, y, z as your coordinates of a particular point or a particular object, anything, under parity operation, let me denote it by p, capital P, x will go to minus x, y will go to minus y, z will go to minus z. Or if you are considering r theta phi, then r vector will go to minus r. The position vector of a point will go to minus r. So, you can ask the question like, what happens to deuteron under parity transformation? So, for deuteron we have the wave function, say psi, denoted by psi. Okay. So, let us consider, or deuteron or any other system, consider a wave function psi r. Okay. So, under parity transformation, under parity, this will go to some psi prime and r will go to minus r. Now, we can ask the question specifically, what happens to the wave function of the deuteron, right. Just before that, let us look at this a little more details. So, psi prime psi r goes to psi prime minus r under parity, and if p is, if the wave function is an even as an eigen state of the parity operation, then you know that the wave function itself will not be changed in its form, but it will just be multiplied by the eigenvalue of the operator. So, let us denote that by some p. So, if I do it once again, okay, so I will actually take this psi prime minus r and apply parity operation on this, and that will take me to one more p. So, p of whatever earlier that we had psi r. So, that can also be written as p square, the original wave function psi r. But what did we do? We first inverted the coordinates, and when we apply the parity operation again, we inverted it again. So, applying parity operation twice will bring x, y, z to minus x, y, minus x, minus y, minus z, and applying it again will bring us back to x, y, z. So, it is as if we have not done anything, we should have come back to the original state when we apply parity operation twice. So, which then tells us that p square psi r should be equal to psi r, which then tells us that p square is equal to 1 or p is equal to plus or minus 1. So, if it is equal to plus 1, then we call it as even parity, that the even parity of the corresponding physical system represented by psi r, we call it having even parity, and if p is equal to minus 1, that is psi r goes to minus psi r under parity operation, then we call this odd parity system. Say for example, deuteron under parity, if the wave function remains the same, then it is an even parity wave function, parity wave function of the parity of the deuteron is then called even, and otherwise we say that deuteron has odd parity. And then again experimentally we can find out what is the parity of deuteron, right. So, it is found that parity of deuteron is even. Now, there is another point here that is related to the, that is how parity is related to the orbital angular momentum. So, relation between parity and orbital angular momentum. So, if L is the orbital angular momentum of a particular system, I can denote the corresponding wave function as say psi L, and it so happens that we can actually show this explicitly, that in this case the parity, the value of the parity is actually minus 1 power L. We know L can take integer values including 0, and therefore, it is either plus 1 or minus 1. If L is an even number, then it is even parity, the wave function corresponding to that will have even parity, and if L is equal to L is odd. So, if L is even, we have even parity, and if L is odd, that will give you odd parity for the corresponding physical system. So, that will tell us that L of deuteron is even, because its parity experimentally is found to be even. Therefore, L is an even integer, and then out of that tells us that L equal to 1, which we said earlier is a possible value for L for the deuteron, is ruled out. Okay. So, that is what we are seeing here. Experimentally one can determine the parity of the particle, and it is found that the deuteron has even parity, and therefore, L is equal to 1 is ruled out. So, the parity of the angular momentum, orbital angular momentum of the NP, relative orbital angular momentum of the NP, neutron and proton inside the deuteron is either 0 or 2 or some combination of these. Okay. So, there are other properties of this deuteron that we would like to consider, but I think we will do that in the next lecture. So, before we actually conclude this lecture, we will pose a question, some simple question which we can think about. Okay. So, we said earlier that the binding energy of deuteron is equal to let us take it to be 2.224575 MeV. By the way, I do not know if I mentioned, but MeV means mega electron volt. So, here mega is 10 power 6. So, the whole thing is 2.2245475 into 10 power 6 electron volt, and electron volt is the energy that an electron acquires when it actually moves in 1 volt potential difference. So, we know that this is the value of this one, and then use this information to find the minimum photon energy needed to dissociate. Now, what is the meaning of binding energy? If you give some amount of this energy to the nucleons, then it will disintegrate or split apart into the separate free nucleons. So, question is, what is the minimum photon energy needed to dissociate a deuteron? Okay, so with that actually we will stop today's lecture.